Good morning, students. So today's class will see about the electromagnetic waves and waveguides. So in this session, we'll just see about the waves in general, and we'll see about the plane waves in lossless dielectric, free space, and good conductor. So first, we need to know what do you mean by waves. So waves are means of transporting energy or information. So typical examples of electromagnetic waves are radio waves, TV signals, radar beams, light rays, and so on. So all the forms of electromagnetic energy share three fundamental characteristics. The first one is they all travel at high velocity, and in traveling, they assume the properties of waves, and they all radiate outward from the source without the benefit of any discernible physical vehicles. So in this session, we'll just see what is the major goal. So the major goal is to solve the Maxwell's equation. So we have studied the Maxwell's equation in the first and the second unit when we learned about the electric field intensity and the magnetic field intensity. In those things, we have also related with the Maxwell's equation using Gauss law, Faraday's law, and Ampere's circuit law. So our goal is to solve the Maxwell's equation and describe the electromagnetic wave motion in the following media. So there are four mediums are there. One is free space, lossless dielectric, lossy dielectric, and good conductors. So in free space, we have three parameters. One is a sigma, where what you call it as conductivity. Epsilon is the permittivity, and mu is the permeability. So for free space, your sigma value will be equal to 0. Your epsilon will be equal to epsilon naught, and mu will be equal to mu naught. And for lossless dielectric, we have sigma is equal to conductivity is equal to 0, and epsilon is equal to epsilon or epsilon naught, where epsilon naught is the relative permeability, and epsilon naught is in free space, and mu is equal to mu r and mu naught. That is, again, mu r is the relative permeability, or sigma will be very less than omega into epsilon. And for lossy dielectric, your conductivity is not equal to 0, and your epsilon will be equal to epsilon r and epsilon naught, and mu will be equal to mu r and mu naught. For a good conductor, your sigma is approximately equal to infinity, and your epsilon is equal to epsilon naught, and your mu is equal to mu naught into mu r, or else you can say for sigma is much greater than the omega into epsilon, where omega is nothing but your angular frequency of the wave. So first we'll see about the wave propagation in the lossless dielectric. So what is meant by a lossy dielectric? So a lossy dielectric is a medium in which an electromagnetic wave, as it propagates, loses power owing to imperfect dielectric. I'll repeat, a lossy dielectric is a medium in which an electromagnetic wave, as it propagates, loses power owing to imperfect dielectric. So in other words, we can say it is partially conducting medium, and it can be an imperfect dielectric, or else you can call it as an imperfect conductor with conductivity not equal to 0. Now we have seen about what is lossy dielectric. Now we'll see what is lossless dielectric. So when we say lossy dielectric is an imperfect dielectric or an imperfect conductor, obviously the lossless dielectric will be a perfect or a good dielectric with a conductivity sigma is equal to 0. Now let's consider a linear isotropic homogeneous lossy dielectric medium that is charge free. So rho v is equal to 0. Assuming and suppressing the time factor e to the power of j omega t, Maxwell's equation becomes, these are the four Maxwell's equation. So del dot Es is equal to 0, del dot H is equal to 0, del cross E is equal to minus j omega mu Hs, and del cross H is equal to sigma plus j omega into Es. Now taking curl on both sides, now first we'll take about the third equation. So third equation is nothing but del cross Es equal to minus j omega mu H. So taking the curl of both the sides of equation 3, then we can write del cross Es is equal to minus of j omega mu del cross Hs. So now applying the vector identity, this is the formula, just note it down. Your del cross A will be equal to del of del dot A minus del square of A. This is the formula for vector identity. Now apply the vector identity to your equation 5. That is only to the left hand side you try to implement your vector identity formula. So in the place of del cross Es, you just substitute del of del dot A minus del square A. So when you substitute it to the left hand side, you will get already one for this side, you have substituted del of del dot Es minus del square of Es. So del of Es is nothing but your Maxwell's first equation, which is equal to 0. So this term will be vanished, only the second term will be there. And the right hand side will be retained as such in the fifth equation. So that is minus j omega mu sigma plus j omega epsilon into Es. Now what you do is, so the first term in this will be vanished. Therefore, the second term alone will be there. So you can write minus of del square of Es will be equal to minus j omega mu sigma plus j omega epsilon into Es. Now we know that del square of Es, making the right hand side has gamma square. That is making the j minus j omega mu sigma plus j omega epsilon. This term, you try to make it as gamma square so that you can simplify the equation. Therefore, both the sides minus sign is there so that you can cancel out that minus sign. So the resultant will be del square Es equal to gamma square Es. So bringing all the equations to the left hand side and equating it to 0, we get del square Es minus gamma square Es will be equal to 0, where gamma square is equal to j omega mu sigma plus j omega epsilon. So for simplification, we have made j omega mu sigma plus j omega epsilon as gamma square. So what is gamma? Gamma is nothing but the reciprocal meters and is called as the gamma is nothing but the propagation constant of the medium. So similarly, so when you write for the electric field, obviously you can write for the magnetic field also. So you can write it as del square Hs minus gamma square H will be equal to 0. So therefore the equations 6 and 8 are known as a homogeneous vector, or else you call it as Helmholtz equation or vector wave equation. Now here you know that gamma is a complex quantity. Gamma is nothing but the propagation constant, which is also a complex quantity. So you can represent the gamma is equal to alpha plus j beta. So we know that from the previous equation, gamma square is equal to j omega mu sigma plus j omega epsilon. So in this ninth equation, when you square it, what you will get, gamma square is equal to alpha plus j beta, the whole square. So when you expand it, a plus b, the whole square formula, you will be getting gamma square plus 2j alpha beta minus beta squared. So therefore, this gamma square will be equal to j sigma omega mu minus omega square mu epsilon. So when you compare this gamma square, where you represented gamma is equal to alpha plus j beta, and what the gamma you got in the right now derivation, both the things when you equate it, when you compare it, you will be getting the real part of gamma square is equal to alpha square minus beta square, which will be equal to minus of omega square mu epsilon. And therefore, if you take this minus to the other side, minus of real part of gamma square will be equal to minus of alpha square plus beta square you will write. Therefore, you will be getting omega square mu epsilon. So just rearranging this, you get beta square minus alpha square is equal to omega square mu epsilon. Now you take the magnitude for this gamma. So when you take the magnitude for this gamma, you will be getting for which gamma, you have to take the magnitude for this equation. Equation 11, you have to take the magnitude. So what you will get, magnitude of gamma square is equal to square root of this j square will become 1, and therefore you will be getting omega square, you will be getting sigma omega mu the whole square, and then this term will become omega square mu epsilon the whole square. So when you take the magnitude for the equation 11, you get magnitude of gamma square is equal to square root of omega square mu epsilon the whole square plus sigma omega mu the whole square. Again, there is a square term over here. Again, you bring the square term inside the bracket, and therefore you'll be getting square root of omega to the power of 4 mu square epsilon square plus sigma square omega square mu square. So when you solve this equation, taking the common terms outside, you'll be getting magnitude of gamma square is equal to omega mu, which is the common term. So we have taken it out into square root of sigma square plus omega square epsilon square. We know that gamma square is equal to beta square plus alpha square also. So you just try to, we have one more equation in the previous case. We have one more equation where you represented beta square minus gamma square equal to omega square mu epsilon. So right now you have got one more equation for beta square plus alpha square. So that previous equation, which is in the 12th equation, I'll just show you again. This is the equation we got. So this is the equation. The 12th equation is beta square minus gamma square equal to omega square mu epsilon. Right now we got beta square plus alpha square is equal to omega mu square root of sigma square plus omega square epsilon square. So both this 12th equation and 13th equation, we can try to solve it. So when you solve it, what you get? You'll be getting 2 beta square is equal to omega square mu epsilon plus omega mu square root of sigma square plus omega square epsilon square. So you just to try to solve for beta. So from this equation, again rearranging, you get beta is equal to 1 by 2 omega square mu epsilon plus omega mu square root of sigma square plus omega square epsilon square. So actually this is beta square. So when you remove the beta in the left hand side, your right hand side will become the square root. And try to take the common terms in the equations. And when you solve it, you will be getting beta is equal to omega square root of mu epsilon divided by 2. So that upon 1 plus square root of 1 plus sigma by omega epsilon the whole square. So the quantity beta is nothing but the measure of the phase shift per unit length in radians per meter, and is called as the phase constant or wave number. So beta is called as the phase constant or wave number. So when you're able to find the beta value, obviously you can find the alpha value. So how do you find the alpha value? We have solved these two equations, right? Equation number 12 and 13. In that, if you change the sign, then obviously you when you change the sign, your beta square will get cancelled, and therefore you will get the answers for the alpha value. So by solving it, you will be getting the value for alpha. So your alpha will be equal to omega square root of mu epsilon divided by 2 square root of 1 plus sigma divided by omega epsilon the whole square minus 1. So you can just view what is the difference between the alpha and the beta. So only this term will be shuffled and the plus and minus sign will be changed. So beta, as beta is called as the phase constant or the wave number, your alpha is called as the attenuation constant or attenuation coefficient. And what is attenuation constant? It is the measure of the spatial rate of decay of the wave in the medium. And alpha is measured in meters per meter, or else you can also measure in terms of decibel per meter. Suppose if you assume that the wave propagates along the positive z-axis, so that the unit vector is plus az means, then your electric field intensity E as only the x component. Then you can write, so far in the equations we have put E suffix S, right? Now what is that ES? So ES is nothing but EX, X in sense it is propagates in the it has only x component. That's why EXS of Z into AX. Now substitute this value of ES in your sixth equation. So in your sixth equation, hope you are also writing the notes, I think. So the sixth equation is nothing but your del square ES minus gamma square ES is equal to 0. In that equation, you have to substitute in the place of ES, wherever the ES is there, EXS has to be submitted. This value has to be submitted. So the main equation, what is the sixth equation is del square ES minus gamma square ES is equal to 0. So when you substitute and take the common terms, we get del square minus gamma square upon EXS of Z equal to 0. Hence, when you expand this equation for del square, what is del square? Del square is nothing but dou square. In the first unit, we have seen del square is nothing but dou square EX divided by dou X square plus dou square EX divided by dou Y square plus dou square EX divided by dou Z square. So wherever in the place of EX, we have substituted EXS of Z. And this gamma square, when multiplied outside, you will get gamma square EXS equal to 0. Okay. Actually, the value of del will be, actually, when you multiply inside, it will be del square EXS of Z minus gamma square EXS of Z. Now, what is del square? Dou square by dou X square plus dou square by dou Y square plus dou square by dou Z square. So when multiplied with EXS, you will be getting dou square EX by dou X square plus dou square EX by dou Y square plus dou square EX by dou Z square. So minus gamma square EX equal to 0. So when you see, as already we have seen that it has only X component, right? So since it has only X component and it takes place in the Z axis, these two terms will get vanished. So when these two terms get vanished, you get only this term alone. So you'll get dou square EXS of Z minus dou Z square minus gamma square EX of Z is equal to 0. So try to take the common terms outside. That is EX is the common term. So you get dou square by dou Z square minus gamma square EX of Z equal to 0. So this is called as the scalar wave equation. Now we'll try to find what is the intrinsic impedance for the lossy dielectric. So far we are seeing the derivation for lossy dielectric only, hope you remember. So what is the intrinsic impedance? Intrinsic impedance, the basic formula is eta is equal to square root of j omega mu divided by sigma plus j omega epsilon. So eta for the lossy dielectric will be square root of mu by epsilon divided by 1 plus sigma divided by omega epsilon the whole square to the power of 1 by 4. So a linear homogeneous differential equation with solution can be written as Ex of Z is equal to, so in the above equation, we had this term Ex of Z. So that can be written as, in a homogeneous way, you can write it as E naught e to the power of minus gamma Z plus E naught dash e to the power of minus e to the power of gamma Z, where this E naught and E naught dash will be the constant. And we know that the field must be finite at infinity, requires that E naught dash will be equal to 0. So if assume it is infinity means you need to have E naught dash equal to 0. Now what in this equation, what is this e to the power of j gamma is it? That nothing but a wave traveling along minus AZ direction, whereas we assume the wave propagates along the AZ. Therefore, E naught dash will be equal to 0. We also insert the time factor. So time factor, whenever you are mentioning the Maxwell's equation in time factor, we have to represent e to the power of j omega t into the equation. And therefore, we get E of Z comma t is equal to real part of Ex of Z e to the power of j omega t into Ax. Therefore, this in the place of E, we try to substitute E naught e to the power of minus gamma Z e to the power of j omega t minus beta Z. That is into Ax, or you can express in the form E of Z comma t equal to E naught e to the power of minus gamma Z cos of omega t minus beta Z. This G term, E term, you can write it in terms of cos of omega t minus beta t Ax. When you can write for the electric field, you can also write in terms of the magnetic field. Therefore, h of e comma z comma t will be equal to real part of, as like the previous case, h naught e to the power of minus gamma z e to the power of j of omega t minus beta z ay, where your h naught is nothing but your e naught divided by eta. And eta is a complex quantity which is known as the intrinsic impedance in ohm. Therefore, eta will be equal to square root of j omega mu divided by sigma plus j omega epsilon, and the angle will be theta n. That is nothing but magnitude of eta e to the power of j theta. So your tan 2 theta n will be equal to sigma divided by omega epsilon. So your theta n lies between 0 to 45 degree, and therefore your h will be real part of e naught divided by magnitude of eta e to the power of j theta n into e to the power of j of omega t minus beta z ay. So this term we can rewrite in terms of cos term. Therefore, you get E naught divided by eta e to the power of minus gamma z cos of omega t minus beta z theta n into ay. Thank you. We'll see in the next class for a good conductor and the other cases, free space, dielectric, medium.